So here's the good news about chapter 5. You want the bad news first? Bad news? It's more probability.
Well, good news is,
Okay, the good news is I think it's actually easier than what we did in chapter 4. So that's why I said maybe we should do the bad news first. It is more probability, but it's what's nice about chapter 5 is it follows a very clear, strict process, and that there's not a lot of all this different rules you have to keep in your head, like the at least ones where you have to know the complements and maybe complements twice and the multiplication rule all combined together. So it's a little bit more straightforward as long as you understand the terminology. So I'm looking at the top of page 56. There's this chart there, which is my first example. We can read up above there, but it may not make sense. Let's try to read it and then we'll look at this example and tie those together. So it's all about what we call probability distributions. Sounds all fancy. A probability distribution, here's my words, is a list where you have some numbers here of all the things that could happen. And then you have the probabilities next to them of how likely that is to happen. We'll go back to the definition in a second. So my first example is if a family has 4 children, and X was the number of girls, it's listed on there. If a family has 4 kids, what are all the possible number of girls they could have? Maybe they have no girls. Maybe they have 1 girl. Maybe they have 2 or 3. These are the only things that might happen. If you ask a family of 4, how many girls do you have? Do you agree these are all the possible answers? And then next to these are the probability of each one of those particular things happening. For example, the probability of no girls in a family of 4. Here's a little review question for you. How would you find the probability of no girls in a family of 4? Yes?
1/2 to the power of 4.
1/2. So the first one's not a girl, the second one's not a girl, and the third one's not a girl, and the fourth one's not a girl. That actually is where that number comes from. Another way you could think about this is we could have made the sample space for a family of 4 kids. The sample space member maybe would be all girls. Oops, only 4 kids. Only 4. I'll have to put a 5th one on there. All girls. Maybe the first 3 were girls and then there was a boy. Or maybe there were 2 girls and then a boy and then a girl. And if we listed all of these, how many things would be in this sample space? How many outcomes are possible? 16. Why? Because that's the denominator, but every time there's 1 child, there's 2 possibilities for the first child, 2 for the next, 2 for the next, and 2 for the next. So those multiply out to be 16. So we could list all 16 of those. And only 1 of those 16, if I wanted to list them all, would have no girls. What would it look like, the one that has no girls? All boys, right? So that one would be over here, maybe be my last one, if I was doing them in order. There's 16 of these. Maybe this one is the one, there's the only one there that has no girls in it. And then maybe we'd go through and say, okay, well, how many of those have exactly 1 girl? And we'd have to count. We did these with 3 kids on the lab assignment last time, actually. It was like 3 out of 8 had 2 exactly 1 girl or something like that. Everyone okay with where we could find all these numbers if you wanted to? List your sample space and count them. So somebody just organized all the possibilities for us in one place. I'm not going to ask you to necessarily create the whole distribution. There'll be times when we do. But you want to just understand that these are all the things that could happen, and this is the probability for each. Okay there? So let's go back up to the definition. It's a description that gives the probability of 4. That's good English. The probability for each value of x, usually in a table, sometimes in a graph. We'll look at graphs later. Probability distributions are very similar to relative frequency distributions. You guys remember those from way back when in chapter, I think it might have been 2. Might have been 1. I think it was chapter 2. What was the relative frequency distribution?
Percentage.
Where you had to turn your counts into percents. Well, if you change percents into decimals, now they're probabilities, right? So it's very similar to the relative that we did before. Here I left them as fractions, but you agree we could turn those all into decimals or percents if we wanted? Then it'd be like a relative frequency distribution. The random variable is up above there. That's the x. This has to be a number. We did some charts like this where you had categories, you know, favorite candies, Skittles, M&Ms, whatever. Those are not numbers. I know you could count how many people like Skittles or M&Ms, but the values over here have to be a random variable that is a number. The very first few questions on your lab assignment or your online assignment say, is this a probability distribution? And if these aren't numbers, the answer is no. Don't even worry about anything else. So your random variable is some number, how many of something might happen. In this case, it's how many girls might happen. Underneath example 6, random variables can be discrete or continuous. So there's some more review words. What are those? Discrete or continuous.
Countable,
Countable is discrete, I like that.
and then there's a decimal and the continuous.
Continuous answers could be decimals. So if I say there's a family with 4 children, could the number of girls be a decimal? I have 3.8 girls. That wouldn't be able to happen. So in this case, this is a discrete example. But if I said, you know, how tall are you? You could tell me that you're 5.5 feet tall, and a fraction would make sense there. So that's what we mean. It could be discrete or continuous. This example is discrete. And then there's these probability requirements, which look scary, but we're going to interpret them. Requirements to be a probability distribution. Here's the first requirement. Somebody tell me what that means in English.
It means sums.
Okay, she says this means sum.
And PX would be those,
PX would be
the probability.
the probabilities, right? Those are all the probabilities. So let's just go with what Kirsty's telling us, right? She says this means sum, and this means probabilities. So somebody tell me an English sentence that this says. Hang on, Kirsty, I know you're all over it. I want to see somebody else got it. Yes, baby.
The sum of the probabilities has to equal 1.
The sum of the probabilities has to equal 1. Equal 1. Everyone agree that's what it says? Yes, Kirsty?
I have a quick question about something you said about the random variables.
Yes.
You said that they weren't numbers?
They have to be
Oh,
numbers.
they have to.
So I said, for example, if I asked you what your favorite kind of candy was, like we had charts like this with, you know, different categories of candy and people who liked each one. Those would not be random variables because Skittles is not a number. And M&M's.
So they have to be quantitative?
Yes, has to be quantitative. So there's, I know for sure there's one problem on the lab where the directions say, is this a probability distribution? If so, then they ask a follow-up question. But if there's categories here as opposed to numbers, the answer is no, it's not a probability distribution. Thank you for clarifying. We okay on that statement? What does that mean? Why does this make sense? They have to add up to 1.
Well, it's like this percentage, how when we did that with the other one. we
The
did,
relative frequency,
It all
yeah.
had to add up to 100%.
Okay, do you remember when we did relative frequencies, which was months ago now, it feels like, that all of the percentages had up to 100%? Because everybody had to be accounted for? So 100%, when you change it to a decimal, is just the number 1. If we add up all these fractions, what should they add up to? 1. The reason they add up to 1 is because if a family has 4 kids, do they either have 0, 1, or 2, or 3, or 4 girls? All of it with an or? They either have 0 girls, or 1 girl, or 2 girls, or 3 girls, or 4 girls. Sorry, what did you say?
They have 4.
They could have 4, but they might only have 2 girls. But they must have one of these things. If they either have this, or this, or this, or it's guaranteed that they have one of these options. And if something is guaranteed, it's certain, the total probability is 1. So the total here equals 1. To verify that, we would have to get a common denominator, add them all up. Let's do that real quick. This is already out of 16. This is 4 out of 16. I'm multiplying by whatever I need to, oops, I made 18 there. Multiplying by whatever I need to get a common denominator. If I multiply this one by 4 over 4, this one by 2 over 2. What do those all add up to? Please tell me it's 16, right? 16 over 16?
Which equals 1.
Which equals 1. If it didn't equal 1, imagine if I said, hey, there's a 20% chance it's going to rain today, and a 50% chance it won't rain today. Some of you are laughing, which is a good sign for me. Let me say it again. There's a 20% chance it will rain, and a 50% chance it won't rain. What's wrong with that statement?
Where's the 30%?
There's another 30% that's missing somewhere, right? And the only options are it rains or it doesn't rain, so where's the other 30%? That you can't not add up to 100% chance, right? So the same thing, your probabilities can't not add up to 1. That means there's something else that could happen. They always have to add up to 1. So that's the first requirement. They have to add up to 1. And then what's the number 2 statement say? This one. How do you interpret this? It looks scarier than it is.
Or bigger than 0.
Say it again, Kirsty, I couldn't hear you.
It has to be equal to or bigger than 0, or equal to or lesser than 1.
Okay, so this says something, you didn't tell me what. Something has to be equal or bigger than 0 and less than or equal to 1.
Oh, the probability.
The probability. This is the probability. Try to put this in some other nicer words for us. English with less math. What's this tell you about your probabilities?
You have to be between 0 and 1.
Greater than 0 and less than 1, she says. What did you say, Kevin?
This is between 0 and 1.
Has to be between 0 and 1, which is what we learned on day 1 of probabilities, right? This is nothing new, it's just the format looks scary because of the notation. This says probabilities have to be between 0 and 1. We already knew that. Unless I can't spell today. So if over here I had, a 1.8 in my table, that's bigger than 1. That can't be a probability. That would automatically make it not a probability distribution. So they have to be probabilities. That's really what this says. Numbers between 0 and 1. And they have to add up to 1. So we agree that this one is a probability distribution. They add up to 1. We check that. Each one is a fraction that's between 0 and 1. So that's a probability distribution. Now, we quite often ask for the mean of this probability distribution. The mean. So in this case, it's the number of girls. If a family has 4 kids, on average, how many girls do you think they have? 2, he says. If there's 4 kids, you would expect that 2 of them would be girls. Now, I know it's not a guarantee, but on average, do we agree that out of 4 kids, 2 would be girls? Some people have more, some people have less, but if you average them, does that make sense? That's what we mean when we ask about the mean of the distribution. So the mean of the distribution here is what's the mean number of girls that we could expect. Here's the deal though. You can't just add all these numbers up and divide by however many you have. It works in this case because of the very specific nature of boys and girls being equally likely. But imagine if it was winning the lottery. You win or you lose. Sometimes you win $1 million and sometimes you lose $1. On average, you don't just say that on average we all win $500,000. Right? I mean, it doesn't work that way. Because why not? Why can't we just average those 2 numbers?
Too many variants.
You might win $1 million. Let's write this out. Too many variables. What do you mean by too many variables?
Well, because you're taking into account what might happen and what will happen, and I don't know.
Same thing.
Yes.
So you either win $1 million or you lose your dollar. We agree with that? And technically you don't win $1 million. You really only win $999,999 because you paid $1 to get in. I better change that. You really only win this much because you had to pay $1 to join, right? So you might win this or you might lose this. That's everything that might happen when you play the lottery. I know there's some other in-between prizes, but let's pretend there's not. If I average these 2 numbers, add them up, divide by 2, it's like $450-something thousand. On average, does everyone who plays get $450,000? I never met those people. Yeah, she wishes. So why can't I just add these up and divide by 2? What's the problem here? Yes.
Is it because you're taking into, like, you can't win and lose the lottery, and that's,
Well, okay, I'm not saying I'm gonna do both, I'm just trying to average this, because those are two things that could happen. You could win or you could lose. So I'm trying to say on average, every time you play, what might happen. And some people are winning and some people are losing. If I add them up and divide by 2, I'm assuming something though, which is not true. Well, I'm not necessarily assuming I'll still get money. Let me ask you a question. Is this just as likely to happen as this?
No.
No, right? You're not just as likely to win this as you are. So they're not equally likely. If they're not equally likely, that's why we can't just add them up and divide by 2. Because for every one of these, how many of these are there? A whole bunch more, right? So there maybe might be one person that wins $1 million, and there's a whole bunch of us who lose $1. So we technically would have to consider all those people as well. So you can't just take those two possibilities, we have to consider the probabilities, which is we're actually gonna do a similar example to this in a minute. Talk about how to calculate on average what happens. But that's what we do when we talk about the mean of the distribution. We also talk about the variance of the distribution, how far away you expect to be from the mean. We said the mean is 2, we're gonna calculate here in a second, how far away. And we can get the standard deviation. I agree that all 3 of those formulas are very scary. I'm not even gonna try to interpret them for you, because we're gonna find all of this on our calculators. We love our calculators. So we have to go back and jog our memories on how to do all this. What I wanna do is type this distribution into my calculator into list 1 and list 2. So we go to stat and edit. Use my computer's open there. Stat and edit. Sounds like Let's jog our memories here.
what are we adding?
The table that we have here that was given to us, these numbers go into the list 1, and these, let me highlight it here, and the second ones go into list 2. So the x's go into list 1 and the probabilities go into list 2. Could you turn off one of those light switches behind you there, Nick?
You just.
Thank you. Let's see if this comes on. See it? Came on. Oh, he just turned it off.
He's up at the custom.
Oh, here it comes. Give it a chance to start up. I want to make sure everyone sees the subtle difference, because depending on which calculator you have, how you get there looks a little bit different. We have to wait patiently. Does everyone remember how to please type them into their lists? And by the way, you can just type these in right as fractions, and your calculator will turn them into decimals as you do it.
So let's do it.
List 1 and list 2. Anyone need me to jog their memory on how to get to that page? So I'm going to go do that real quick here. So I'm going to go to stat, tell what I want to edit, and I have 0, 1, 2, 3, and 4. And then over here, try to always use my, no, because I can't do it on here. 1 divided by 16, so I'm actually typing in 1 divided by 16 right here. But when I hit enter, it turns into a decimal, which is fine. My next one was 1/4. I'm going to cheat and put into a decimal right away because I know that one. The next one is 3/8. And then 1/4. And 1/16 again. So I have all those in there, list 1 and list 2. Again, just like we did before back in chapter 3, when you want the mean, we're going to use one of our stats. That hasn't changed. So we're going to go back into the stats button here. Stats. We're going to move over up here to where it says calculate. Remember that? It's been a while. We're going to be doing heavy calculator use pretty much every day from now on. One of our stats. Only hit enter once. Now, if you have my calculator that looks like this, some of you don't, some of you have something else, so we'll pause if you don't have this. If your calculator looks like this, we need to tell it that list 1 is my x's, which we already have there. You see where it says frequency list? we know we need to tell it to look at list 2. So I'm gonna come down here. List 2 is in blue down here above the number 2. So I have to hit the second and then the list 2. If you don't have this screen and all you have is a 1-bar stats typed on your screen, I can't show you yet what it'll look like. It's gonna disappear. Some of you have the calculator that only just says 1-bar stats. It doesn't have this pretty screen. 1 second, Kirsty. Then you're going to type in L1, comma L2 right after that before you hit enter. Yes, Kirsty.
Oh, no, I was saying I have that one.
Oh, okay, if you have that one. Everyone know how to find the L1, the L2, and the comma? So you're either typing this, or your screen looks like mine up there. Everyone have one or the other?
What did you say? If you have the 1-bar stats, what do you have to type?
So once you have 1-bar stats showing on your screen, then you type L1, comma L2 before you hit enter. So right next to where it says 1-bar stats. Do you see how to get there? Or not? Yeah? If you do this and then we go down to calculate, or the rest of us hit enter over here,
So it's just like formatted differently. I was like that.
calculate, we get this. So I want to know if we can all get to this screen. Can you see that, Nick? Is it too big? We're good?
Yeah.
Anyone having trouble getting here? Do we have this screen now? Everyone's there? What does this tell us? What's that X bar tell us? The mean. Remember we already said we're pretty sure the mean is 2 here. Remember we said the average number of girls we thought would be 2? So the X bar is the mean. If I ask you to find the mean of a probability distribution, guess what you're going to do? Use your calculator and know how to read it off the screen. And again, on an exam, I will always tell you how to use the calculator. If you're telling me I can't find 1-bar stats, I'll help you find it. If you tell me I've got these 2 lists and I can't remember how to type that in, I will always help you with your calculator. So there's the X bar. What else is on this screen? Look at the SX is blank. The SX is blank. I don't know if you recall, way back when in chapter 3, I said we're always going to use SX. SX is the one that we want when we're finding the standard deviation. And I said there's one exception when we won't use it. Today's the day. Guess why we're not using it? It's not there. Because SX is from the sample. And this probability distribution actually represents the entire population. This represents all possible families of size 4. There's nobody left out here. It's all the possibilities. So instead of SX, we're going to look at sigma X. What is sigma? I hear some people quietly saying it. Somebody confident enough to say it? Louder? I hear everybody whispering. The circle thing, yeah, it looks like this, but what does it represent? The population, standard deviation, thank you, teamwork, we like it. That's the population standard deviation. Which in this case is 1. Now, our calculators gave us X bar equals 2. But look at what our formula is asking for. The mean has a mu in front of it. You see that on the formula in the middle of page 56? It's supposed to be a mu. What is mu? Population mean. So that's the one restriction, is our calculator doesn't actually ever write the mu. It says X bar, but that is your population mean. So for this example so far, the average number of girls in a family is 2. And we expect most families to be away from that by 1 on average. Maybe they have 1 more girl or 1 less. It could be further away, but typical families have 2 girls, families of 4, have 2 girls with maybe 1 more or 1 less. So now that we're getting our calculators figured out, Christian had a really good question. You will be asked for the population mean, which is mu, but the calculator will call it X bar, which we know is really the sample mean. So even though we want mu, the calculator calls it X bar, but that is our mu when we're doing probability distribution. Questions about mu versus x5? The reason we had to care about that in chapter 3. And what if I wanted the variance? What's variance? Who remembers that?
Yeah.
Before you round it? What's the symbol? Okay, but we're not square rooted here. Our calculator did it. What's the symbol for variance? Something squared.
I think it's like the.
Yeah, it's sigma squared. Sigma squared was the variance. Someday you might want to go back and review your chapter 1 through 3 test. Because everything in there is going to keep coming back. Sorry, what did you ask me, Jenna?
Oh, no, that's just a.
So in this case, it's 1 squared, because we already have the answer for it. You will never see the variance on your screen. You have to take your standard deviation and square it. You had to do this back in chapter 3. You just chose to forget it all. So in this case, it's also 1. This is the population variance. So I will never refer to those formulas asking you to find the population mean, standard deviation, or variance. I'm going to assume that you can use your calculator. If you're doing these problems online on my stat lab and you say, help me solve this, it's going to tell you to use the formula. It doesn't know that you have the fabulous calculator. So make sure you're putting really good notes in your notes that you're taking right now, saying, hey, I can always do this on a calculator. Can you not read it, Kirsty? I see you squinting up here.
I'm waiting for my glasses
Oh.
to come, so I'm like,
Oh, no.
disadvantage of them.
Questions here? I think we're good there? Okay, at the bottom of the page, can you turn the other lights back on there, please? Thank you. I think we're about to do more calculators, so I'm going to leave this on for the moment. But the round-off rule hasn't really changed. We didn't have to round this at all, actually, because they were whole numbers. And again, I'll tell you where I want you to round. Tell me what you want me to read to you, Kirsty.
Oh, no, I just got it.
You got it? Okay. You can't read it, then just let me know. And then see where it says unusual at the bottom of the page? We've been crossing off the word unusual all semester long. What have we been replacing it with? Aha, significantly low or significantly high. Bottom of page 56. Cross off the word unusual and change it to significantly high or significantly low. And do we agree that's the same definitions we've been using all semester? More than 2 standard deviations away from the mean? So we would do 2 steps below or 2 steps above and see if we were further away? So this part hasn't changed. There's another way we can tell if something is significantly high or low. It's not written here. It's if your probability is so small that the event is unlikely. For example, I talked before about my coin that I flip 100 times and I get 99 tails. What do you think the probability is that I will get 99 tails out of 100? You can't actually calculate it, but if you had to estimate it. It's really unlikely. You expect it to be a really tiny probability, maybe 0.000000. It's possible, but highly unlikely. It's so small, it's definitely less than 0.05. So that's unlikely to happen, which means that 99 must be some significantly high number of tails. So significantly high is far enough from what you expect, but also the chances of it happening are really low. We'll talk about that as we go today. Or a low probability. Is 4 a high number of girls to have? Is 4 significantly high?
Yes,
Yeah? Why yes?
that's a lot of girls.
It's a lot of girls. Okay, it's not a judgment call, it's a statistical question. Significantly high is more than 2 standard deviations away from the mean.
Yeah, because it's 2 exactly away from the mean.
Ah, so is it more than 2?
No, it's exactly.
Aha. So let's talk about that. The mean was 2. 1 standard deviation away would take me to 3, and another standard deviation would take me to 4. So if they had more than 4 girls, that would be significantly high, and not to mention impossible. But 4 is not significantly high, because it's right on that cutoff. Right on the cutoff. It's not more than 4, it is 4. And what is 1/16 as a decimal? Can someone divide that for me? 0.0625. Is that an unlikely probability? Definition of unlikely
Has to be less than.
has to be less than 0.05, 5% or 0.05. Is this less than 0.05?
No.
So that's not unlikely. So it's not unlikely to have 4 girls, which means 4 must not be significantly high. These words are going to get interchanged a lot. If something is, the whole reason we keep asking you, is this likely or unlikely? Is this so unusual that we say this is really high or really low? So that's not less than 5%. Not less than 0.05. So it's not unlikely. I'm about to pass back the quiz from last time where a lot of you got this part wrong. You said, oh yeah, that is unlikely. It's not more than 2 standard deviations away from the mean, and it doesn't have a probability less than 0.05, so it's not unlikely. I agree it's less likely than some other things, but it's not, if someone says, wow, this family of 4 kids had all girls, you wouldn't be like, wow, that's really strange. Or imagine if they had 10 kids and they were all girls. Then you might be going, you know what? 10 girls is really unlikely. There's a certain number where all of a sudden it seems a little bit more odd, right? Other questions, comments? Getting there? Okay.